So the first slide, sorry about this. This was the outline of the talk. So the first slide is this. I'm going to go through it again one more time just to make sure that everything is covered. So I was just mentioning that uh, the single event effect happens when a charged particle like a neutron or an uncharged particle like a charged particle like a proton or an uncharged particle like a neutron hits an electronic circuit, and along the way it generates these electron hole pairs that you can see here. So this could potentially disrupt the operation of the circuit or destroy the circuit. Many of satellite instruments, they all actually have electronic circuits on board, such as FPGAs, power MOSFETs, EPROMs, etc. And these devices could be affected by the strike of charged particles. So one needs to test them prior to launch and find where are the weaknesses in these circuits, and basically come up with proper measures either to change the design to remove this weakness, or if not, do some radiation hardening, uh, change of circuit design or radiation hardening, such as silicon on sapphire or silicon on insulator. So, where are the sources of these charged particles in space? The cosmic rays is one of them. Let's say if there's a supernova explosion somewhere in one galaxy, it could send a lot of charged particles towards our solar system, and the protons and heavy ions could come to our atmosphere and bombard the satellites. And the other source is the sun, where especially during solar flares, it sends all these protons and heavy ions towards towards our planet. And some of these charged particles, they are trapped in the Earth magnetic field and they form the Van Allen belt. So when a satellite is traversing through these belts, it gets bombarded by these charged particles. You also have a secondary particles as is shown in this picture. So when a secondary cosmic particle, a primary cosmic particle hits the atmosphere, it could generate this cascade of secondary particles that you can see, the muons and other particles. So that's the third source of generation of these particles. So some basics about different types of single event effect. You have the non-destructive effects such as single event upset, single event transient, single event latch up, and single event functional interrupt. And we also have the destructive or hard errors. Single event latch up could also be hard error or destructive, single event gate rupture, and single event burnout. So here in the diagram, you can see, for example, a charged particle is hitting a cell in an SRAM and is turning its value from 0 to 1. Here, another charged particle is hitting a logic gate, and it creates this transient pulse that propagates down the circuit, and eventually it hits another cell and flips its value from 1 to 0. So SCU and SCT in action. So more of these soft errors, we already explained SCU and SCT. What about single event latchup? So basically, it always is accompanied by increased current flow, and the chip will heat up, and there will be upset bits that may lead to disruption of the circuit operation. One way to get rid of this, if it is a non-destructive SCL, is to do power cycling, and this will go away. Uh, the other effect is single event functional interrupt, which happens when a, a, a charged particle hits the control bits, and it causes some soft error that causes the component to lock up or malfunction, but it doesn't require a recycle of the power. You can just basically reset the circuit, and then it will go away. So it's not accompanied by high current and heat, unlike SCL. Then we have the destructive SEE. The single event latch up could also be destructive, and that is when even the power cycling would not uh, basically they remove the error, and still, for example, you cannot write a 1 on a cell. If it's flipped to 0, it stays as 0, so it's damaged basically. And then the other is the single event burnout, which happens in DC to DC converters and power MOSFETs. You can see here there's a visible burn and basically destruction of that component. We also have the single event gate rupture, SEGR, that happens in MOSFETs. So you know in MOSFETs you have the source, the gate, and this and the source and the gate are shown in here, and the drain. That's what I want to say. Source, the gate, and the drain. So these are insulated from each other. There is a die that separates the two. So once a charged particle hits, it could generate electron hole pairs that basically would ionize this insulator, which is the die in the gate, and the electric field due to this could add to the to the gate's voltage and cause a breakdown, and it gets shorted out and destroyed. So the interesting part is that we can only trigger this effect by the particle and not by the optical method. I'll talk about the optical method. And I just wanted to explain why that is the case. This is the only SCE that cannot be triggered by an optical uh, visible or near IR lasers, for example, is because in order for this to happen, the insulator needs to be ionized, and the typical near IR and visible lasers do not have enough energy to ionize the insulator. So you cannot trigger this with the optical method. Maybe if you use X-ray lasers or UV lasers, some of these MOSFETs could be uh, showing SCGR, but with the ordinary lasers that we use, you cannot trigger that. So that's out of question to get SCGR. So the need for testing the satellite instruments prior to launch, uh, we need to identify where the sensitive nodes are. So for example, here in this SRAM, you can see in this SCU sensitivity map, there is a sensitivity map. The red are the most sensitive spots, and the yellow correspond to less sensitive spots. So these have been identified by particle testing or optical testing, and one has to come up with either redesign or measures of radiation hardening to cover these spots so that the instrument does not have any problem when it goes into the orbit. So the radiation testing foresees the standard method of testing. So beam of charged particles are generated in a particle accelerator and are basically impinging on the electronic circuit, which is in a vacuum chamber. So there are pros and cons of this. The pros are, first of all, they're more realistic of the space environment, because what really is bombarding the the circuit is charged particles. They can penetrate through metals, and the parameters of SCE testing, such as absolute saturation cross section and upset threshold, can be measured accurately. Also, realistic error rates could be measured. However, the bottom line, the downside is that they're expensive, and you require a long time to get an appointment to go there. You may have to wait for a few months, and they may damage the circuit permanently, and they don't penetrate through protecting insulated layers, such as in flip chip packaged IC. These charged particles could not go through these and reach the sensitive part. You also need a vacuum for the measurement, because otherwise the charged particles will collide with the air molecules and lose their energy. So here is an example from a facility in Finland, and you can see this very long tube where the charges are being accelerated through a high electric field, and they come at a very high energy and hit this electronic circuit that is inside the vacuum chamber. They usually make an ion cocktail of 7 different types of particles, and they test it, and I want to send you a video. Also, I did not mention that our platform, the GoToMeeting, is not really meant for sharing videos. So for this reason, I would like to share the link for you guys, and you can watch this later. I will only show one video when I'm introducing uh, the C system, the SE system in our company. So that's what I would like to basically send you right now on the chat, so you could watch this later. Okay, so this is the SE radiation facility in Finland, and then once you go there to this radiation facility, they would do the testing, and this is a standard curve that is generated, the saturation, the cross section versus the LET, which is the linear energy transfer. And this linear energy transfer is basically proportional to the stopping power of the material against the bombarding radiation. So the more the energy, the more the stopping power, and the units are mega electron volt centimeter square per milligram. So initially at low energies, the cross section is zero, but at some point it rises, and that's the threshold let, and it rises, and at higher energies it flattens off. So this is a saturation cross section. So these parameters are important for SE testing to measure, and basically to get the cross section, which has a dimension of centimeter square for an accelerator test. One can divide the number of upsets that are shown in red here by the fluence of the beam, like particles per centimeter square, and which are shown by these arrows. And then you can calculate the centimeter square and get this typical curve for SE testing. Now, we go to the optical method, which is the focus of this talk, and what our company offers. How is it different? So, instead of bombarding the circuit with particles, high energy particles, one can basically focus an optical beam to a micron size diameter and shine that on the circuit. So, this is the basic system for optical method. So you can see there's a laser system, and then you have illuminators to illuminate the chip. The chip is mounted on a positioning system, very accurate positioning system with a micron resolution. And you have two types of camera, a CCD and a shortwave camera are illuminating it to tell you where you are. The microscope objective is focusing the beam to a micron diameter size, and this way you have many advantages of using this in place of the particle method. First of all, it's less expensive and can be done anywhere, and you can buy a system, bring it to your own company, do the testing, and no need to wait for 6 months to go to a particle facility. It passes through thick insulating layer, for example, in a flip chip. So the particle could, the optical beam could pass through that, and one great advantage is the spatial resolution that you get, because the particle beam is wide, so you can't get the spatial resolution. But this is a micron size diameter beam, so you can specifically see where the the the, the upset has occurred. And you can also get temporal information by synchronizing your detector to the laser pulse. No vacuum is required for this, and but since nothing is perfect, the there are also cons for this method. And one uh, downside is that you cannot measure absolute threshold and saturation cross section. Basically, these need some calibration against a particle method. So the absolute values could not be measured. It just produces a relative value. It does not penetrate through metals, unlike the particles, and it's only a complementary method to radiation testing. It's not supposed to replace it. Most of the people who use this are basically preparing to go to a particle facility, so they identify all the errors, they test different part of the circuits, and many times you realize even without going to the facility, particle facility, you can do a redesign of the circuit or do radiation hardening. And then for final calibration, you go to a facility. This way, you reduce the time that you spend on that facility, and also you save the money that you spent there. So, some basic physics which I want to mention because it's related to the laser, the choice of laser that we'll use. So, I'm sure you're all familiar with different band gaps in metals, semiconductors, and insulators. So in insulator, you have a wide band gap, and in metals, you have overlapping bands. But in semiconductor, you have a band gap that is possible for an electron hole pair to jump across. So so for silicon, this is about 1.1 electron volts. And if a photon or particle hits an atom in the valence band, it could generate an electron hole pair, and the electron could jump to the conduction band and contribute to the conduction. So so this means that uh, the energy that is corresponding to the band gap of silicon is 1.1 electron volts, is about 1100 nanometers. So if your wavelength is below 1100 nanometer, you could get absorption, and you could generate the electron hole pair. So if you do this experiment in the with the photon instead of a particle, you get exactly the same type of curve, cross section versus energy, but the unit of energy here is picojoules. Uh, it's not LET. So you can measure the upset thresholds and the cross sections, but you may need to go to a particle accelerator to calibrate this to get exact values. Uh, for measuring the cross section in a optical method, one has to move the beam within one cell, and basically every time there's an upset, you could reset the circuit back to its initial value and then explore other parts of the circuit. At the end, when you cover the whole circuit, then you could multiply the number of upsets by the size of the beam, and that will give you the cross section. So here is an example of that. You can see the picojoules is the x-axis and the centimeter square is the y-axis. Now, penetration depth in silicon increases with increasing wavelength. So, for example, for 590 nanometer is only 1.7, but at 1064 nanometer is 676 micron. So, in order uh, to go through the backside and a thicker layer, you have to make sure you use a laser that has enough penetration depth to pass through that area. So this is uh, uh, this is a curve of absorption coefficient versus wavelength, and you can see absorption coefficient decreases with increasing wavelength, and past 1.16 micron it drops to zero. So past this, the photons do not have enough energy to lift the electron from valence band to conduction band. So we get to the single photon absorption, optical excitation of carriers. So here you can see the band gap, EV, and EC is the conduction band. This is the valence band. So if you have a photon of 590 nanometers, it could create an electron hole pair. The electron could jump to the conduction band. So these interaction of radiation with matter is described by this set of equations. And you can see that for the basically the single photon absorption, uh, only the first term matters. The other terms are negligible. They're higher order terms that we ignore for the single photon absorption. So we only look at the first term. This is the rate of change of intensity with distance, and this is the rate of deposition of charges. They both depend on the intensity of light. So if you look at this term, this would turn into a very familiar Beer's law, which is the exponential absorption. So we're all familiar with this. And the charges they propagate, they're generated in 2 dimension, and penetration depth increases with increasing wavelength. It's actually 1 over alpha, the absorption coefficient. So for two different wavelengths, 590 and 800 nanometer, the red is showing the deposited charge, or 1 over E contour, which means 63% of charges are deposited. And you can see for a larger wavelength of 800 nanometer, the penetration depth has increased. This is about 7 micron, and this is less than 2 micron. Here's again the same thing. And you can see at this point, the intensity has decreased to 36% of its initial value, and 63% of the charges have been deposited. Now, what about the effective pulse width in SCE testing? Could we use any pulse width, or does it matter? Basically, this very interesting paper that is given here uh, by Duane in IEEE. So it talks about 3 regimes of pulse widths. There is a 100 femtosecond to 30 picosecond region here, where there's no dependence of threshold pulse energy on the uh, on the pulse duration, so it remains constant. And this is because this duration is less than the response time of normal circuits, so it doesn't change. Past 30 picosecond to 8 nanosecond, there's a gradual rise in the energy, so energy increases with increasing pulse width. And past 8 nanosecond, there's a sharp linear rise with increasing pulse energy. So it is definitely better to use a picosecond laser for inducing the SCE, but you can also use a wider pulse, but you would need more energy. Now, how about two different methods of illumination, the backside and the front side illumination? So if the circuit is covered by metals, you can not basically use the optical method to do the front side illumination. You need to go through the backside. And here is the example of a flip chip circuit. So it's gone through backside, but one has to make sure that the penetration depth is larger than the thickness of the die in the backside. And if that's not the case, then one has to be able to polish the backside of the circuit of the chip so that it becomes reachable by the beam. Now, we talked about single photon absorption. Now we're talking about the two photon absorption. This is when the energy of the photon is less than the band gap. It's actually should be slightly more than half the band gap. So for example, a 1260 nanometer beam. And in this case, you use a very short pulse of the femtosecond duration, and you focus it to a very narrow spot, and the energy should also be larger. It should be in nanojoules, whereas for the SPA you could use picojoules. In this case, you should use nanojoules. So basically, the nonlinear effect will kick in, and in this case, you will use the higher order term, the I square term instead of the I. The other terms will be negligible. So the I square term comes into picture, and these two photons would put their energies together to generate the electron hole pair and excite an electron from the valence band to the conduction band. So you can see the schematic in here. While the beam is not focused, there's no uh, generation of charges, unlike the SPA where you have generation of charges along the way. In this case, the generation of charges only at the focus. So this way you can basically inject electron hole pairs at a particular depth that you can choose with the focusing of your beam. And the advantages is the propagation of charges are in 3 dimensions. You can see this is where the charges are generated, uh, and it's more similar to radiation testing. uh, so as I mentioned, the pulse should be short, about 120 femtosecond, and the energies are higher, about 1 nanojoules. So you can focus the beam only at the point that you like. You don't have to generate these electron hole pairs along the way, uh, which is the case for SPA. So when you want to compare the TPA versus SPA, there are advantages and disadvantages. The advantages of TPA is that it has large penetration depths. It's more similar to radiation testing. Back illumination is easier. Carrier confinement in the focal zone and 3D imaging is possible. On the downside, the the because the lower resolution for the microscope due to larger wavelength. So as the wavelength increases, the diffraction limit causes the resolution to decrease. So 1260 has lower resolution than say 1030 nanometer. Then there is the additional components for the femtosecond laser. You need to introduce an optical parametric amplifier, which costs more. And also due to this inhomogeneity, if there is any inhomogeneity at the back of the chip, this would cause the changes in the charge produced in the sensitive volume. So one has to make sure that the backside is very homogeneous, very flat, and also make sure that the laser intensity it does not fluctuate because it's a nonlinear effect. It's proportional to the square of the intensity, and these fluctuations could alter the results. So to quickly summarize the necessary parameters for the laser, we talked about the wavelength that past 1.16 you cannot get single photon, and then you would have to go with 2 photon. The longer the wavelength, the deeper the beam penetration. We talked about that. The pulse duration, we talked about it on 3 different regimes that exist there. The pulse energy, SPA, usually picojoules, TPA nanojoules, and analog circuits normally require more energy than digital circuits. And as far as the spot size is limited by diffraction. For the system that we'll introduce, we had about a 4 to 5 micron beam with 100 times microscope objective. So obviously, that the smaller the beam is, the higher is the resolution. All right, so let's go and introduce our system. After all this theory, I wanted to focus more on the results and introduction of our system than basic theory. So this was the system that was built by Allied Scientific in 2015 for a U.S. aerospace company. It was a SPA system with the potential to be upgraded to TPA. Sorry. You can see it's a little bit bulky, but this was our first attempt to making this system. This was sold to the aerospace company in the US. And the new systems that we have, there's a schematic in here that describes the 4 subsystems of this system. There is the laser subsystem with the 1030 nanometer near IR laser. It has a number of polarizers and neutral density filters in front of it. And also, you have the uh, CCD systems, You have a visible CCD and IR CCD. Then there's the illumination system, which consists of an IR LED at 1300 nanometers and a visible LED at 625 nanometer. And finally, you have the microscope objective plus translation stage. We have two microscope objectives, 100 times and 20 times, and the translation stage of 1 micron resolution. In the XY axis, in the Z axis, we have a 30 nanometer resolution because we use a Newport piezo actuator. So this is a schematic of our system. Um, and in order to understand it better, there's a video here that I'm going to share right now. So our company CEO, Mr. Steve Lavoie, introduces our system. So let's watch this together. I'll send you this link first so you can have it. And if you like to watch it later, you can do that. But in the meantime, I will also play that. I'm sending you this, and I will also play that video. Okay, so this was the introduction of our SCE system by Steve. So all the controls are computerized. We use LabVIEW program to adjust the power of the laser and also control the translator. So let me introduce a little bit further. These are the parameters of the two systems. The SPA, typically 30 picosecond pulse width, and is capable of producing 3 microjoules per pulse, but there are polarizers and attenuators that would bring it to a lower level, picojoules. And in case of TPA, we have about 150 to 250 femtoseconds, and basically you can have nanojoules of energy. You can see that the TPA system has this extra component, which is the OPA, the optical parametric amplifier, and one can use the 1030 nanometer SPA for pumping this OPA, and that could generate wavelengths from 630 to 2600, and you could choose a wavelength for operation of TPA. So for this reason, it's possible to upgrade from SPA to TPA, where you can buy a SPA system with a 1030 nanometer, and then if you later decide to do a TPA to upgrade it, you would just get this OPA as an extra unit, and you have to maybe modify some of the optics, but you can upgrade it to TPA. So this testing station is available for rental. So in case anyone wants to come and to test their equipment, it's possible to come and rent this facility. And we also build and sell commercial grade SE laser stations for both SPA and TPA. So let's look at the requirement for testing of wide bandgap semiconductors. Although we haven't done any testing for any of these dyes, but they have larger bandgap like gallium arsenide, 1.42 electron volts. So one can use titanium sapphire laser, which is a tunable laser in this 720 to 1000 nanometer. For gallium nitride, very large band gap, 3.4 electron volt. So a 364 nanometer UV laser, excimer laser could work. And for silicon carbide, 2.3 electron volts, neodymium YAG second harmonic could work. Although we haven't built any of these, we are capable of building for other material in case there's a customer. But so far, all the systems we have built is for gallium, is for silicon. So let's look at some of the results, some of the case studies that we have done. So as I said, we didn't want to test any new devices. We just wanted to validate our system by testing a chip that whose uh, SCE effect was known and was in the literature. So we chose this HM6504 that was tested by McMorrow, Pouget, and Buckner uh, a few years ago. And you can see that this is a 64 by 64 SRAM cell. And the square is showing one cell, and these are the metal parts that are covering part of the cell. So basically, what these guys did was they moved the particular laser energy, they moved the beam throughout in a raster throughout the cell, and every time they saw an upset, for example, one drop to zero, they reset it back to one, and they moved to another point, and then they once they covered the full cell, then they multiplied the number of upsets by the area of the beam, and that would give them the cross section. Then they changed the value to another energy, higher energy, and you can see higher energy produces more upsets. And here at 20 picojoules, you have more upsets, and eventually it should become flat, which will give you a threshold, basically a saturation cross section. So this is what we are trying to repeat, but with our laser, which is at 1030 nanometer, not like their laser, which was 800 nanometer. So the first step was to get a hold of ceramic chip because it's easier to decapsulate it. You can just remove the cap using uh, a side snip plier, very easily done. Unlike plastic, which you need some acid etching to remove it. So you can see the silicon is exposed here, and here you can see the schematics. This is the memories. These areas are the memory cells, and these are the sense amplifiers and column decoders. So there, it is all divided into different sections. So what we did was Here are the components of our system. First of all, we mounted this decapsulated chip on an Arduino board, so we have control over reading and writing on it, and we wrote a 1 to all the cells. So the Arduino software is also reading. Here you can see the cell number and the value on the cell, which is 1. So all of it was 1, and then we had a switch box here that would basically switch between read and write, or writing a 1 or writing a 0. So instead of running the software, you would just switch it and then it will automatically write. Here is the translation stage, X, Y, and then the Z is in this one on the top. Here the LabVIEW software for controlling the motion of the translation stage, and also for the power of the laser. You can also see the cells of the SRAM in the image on the camera. You can also see the laser beam where you are. So we used two different microscope objectives at 20 times and 100 times. Uh, the size of the laser at the aperture of the microscope objective is 7 millimeter. So it passes through the 20 times because it has an 8 millimeter aperture, but is partially blocked by 3 millimeter aperture 100 times. So we get less energy going through the 100 times, although you get more magnification, but you get more energy with the 20 times. Uh, so here is the results of the settings of the SRAM testing. We use a laser rep rate of 10 kilohertz. Although this was a little high, if we were doing it again, we would probably choose a 1 kilohertz, because 10 kilohertz may be a little too high. So you need to give enough time for the cells to recover after they've been upset. So but it worked anyway. Laser pulse width 30 picoseconds, and the pulse shape was selected as single pulse. You can also get multiple pulse with our laser system. Uh, Laser pulse energy varied depending on microscope objective. Initially, we wrote a 1 to all the cells, and after illumination, we detected which cells turn into 0. Uh, we used a defocused beam because we wanted to do this faster. We didn't want to go through only one cell, just like Buckner, because we are not doing the measurement of sigma versus the the energy. We just wanted to see how easily the sets the cells get upset and how many cells get upset. So our beam was 400 micron diameter instead of 5 micron. It was defocused. Both 20 times and 100 times microscope objectives were used. So this is the full video because we did a live demo of this for the SEMAPLD virtual conference. So I'm going to go ahead and send you this link in case you want to watch it later to see the result of our experiment. I'll send it over the chat to everyone so you can watch that later. But I'll go through the results of this. Uh, so, so the first test was we had used the 100 times microscope objective, and we had a 13 nanojoule pulse energy. Why so high? Because this was a defocused beam. So if you would scale it back to a 5 micron diameter, you would get picojoules, which is typical of SCU, which we wanted to detect. So we moved the beam along this inverted L-shaped, first up and then to the right, and we moved the translation stage by about 200 micron steps along Y and then X. And we monitored the live feed camera. So after illumination, we did a read, and we saw that some of the cells were upset. So here you can see cell 719 was 1, and cell 720 turned into 0. So this was an upset. And also 847 was 1, and 848 was a 0. This was another upset. So in total, we got 8 cells that were upset, and these were inside the range of illumination or the region of illumination by the laser. So we, we could also write one back after these turned to zero, so the chip did not get hot, and we could also rewrite easily. So this was a clear indication of an SCU. Then we increased the energy to 60 nanojoules, and again moved the beam in this inverted L shaped, and we saw that many cells were upset. Even some of these cells that you can see in the red color were not in the region of illumination. They were still upset, and the chip got very hot. So obviously large current was passing through. So we needed to stop and remove the power, recycle the power, and after recycling the power, we could write a 1. Prior to recycling, we could not write anything because the chip was extremely hot, and it just was in a state of latch up. So this was a single event latch up. When we tried this again with writing a zero first, initial value zero, and then illuminating with a 60 nanojoule pulse energy along this L shape. And again, we saw a similar effect that basically these red are now ones, whereas in the previous case there were zeros. Now they're ones. So these were all the upset cells. And again, chip got very hot, and we had to recycle the power, and then we could write a 1. We could write a zero, sorry, we could write a zero in this case to all these upset cells. And finally, we increased the power to pulse energy to 500 nanojoules. The initial value was 1. And you can see all these red cells were generated, lots of upsets. So more than 60-70% of the cells were upset. And after uh, removing the power and recycling the power, we still could not write a 1 to these upset cells. So that was a clear indication of a destructive cell, because even the recycling the power did not solve the problem. So it was still sitting at 0, and we could not write a 1 to the upset cells. So, what is our future course of action? Uh, Maybe we could, uh, if to do the testing, we could focus the beam to 5 micron diameter and do a quantitative measurement of the absorption cross section, saturation cross section, and the threshold, because we have to move the beam within one cell. And uh, we can also shine the laser on the control electronics and check for upsets. For example, you can see when I was showing these are the control electronics. So we shine it only in this area in the memory cells, but we want to shine it on the control electronics and see if we can see Cepheid instead of SCU or cell. And probably use a lower, uh, basically a lower frequency, like a 1 kilohertz instead of 10 kilohertz. The second test that we did was with LM124 op amp. Again, this was uh, very well documented in the literature, and you can see the schematic of the circuit. There are several transistors, and one of the transistors, Q9, is very sensitive to upset. So again, we decapsulated this. This was also a ceramic chip. We decapsulated it, and then we mounted it on a follower circuit using a picofarad probe, basically. And this is the image of this circuit that you can see in our camera. And you can see that it's exactly the same. Here is the Y is tilted towards the left side, and here the Y is tilted towards the bottom. So this is exactly the same circuit as this from the literature. Uh, we used the 260 nanojoules pulse energy at 10 kilohertz, and we also triggered the scope using the 10 kilohertz sync pulse from the laser that you can see in this scope picture. Then we saw these set pulses that had different shapes appearing and traversing through the scope. You can look at it in the video that I sent you. So these set pulses were detected, although we didn't do any quantitative measurements, because one can do the amplitude of the set pulse versus the bias voltage. We only used the one bias voltage. And so hopefully for next time, if you're trying this, we can do some quantitative measurements. Finally, I want to show you an Allied Scientific's fully installed and commercial SCE system. So you can see we sold this system to Germany, and it's all enclosed uh, in this basically box. Is well protected. This window is a class 4 protected window, so laser class 4 could not pass through this. So everything is enclosed within these shelves, and you have, these are all the optics, the lasers, the translation stage, controllers are here, and there are two cameras. This is a visible camera, and this is the near IR camera monitor that is looking through this. So our capability is to build SPA system and or SPA system with the possibility of upgrade to TPA, or a TPA system at 1240 nanometer, which uses the OPA. So some customers are very sensitive about protection, eye protection, so they wanted this to be enclosed in a box, in a shelf that basically could be enclosed completely and no possibility of leakage of radiation to outside. So this is what we sold to Germany. So in conclusion, what we saw that the SCE laser pulse testing is only a complementary to radiation method, but it's very useful for finding the errors, the types of errors before going to a radiation facility, and identifying these errors and maybe modifying the design or do radiation hardening. Uh, so TPA, we compared the TPA and SPA together, and we found that TPA is more expensive, but in some applications it's easier to do backside illumination, and is more is closer to a radiation testing than SPA, because the charge track is more similar to SP to a radiation testing, to particle testing. Now, optical SE testing systems definitely are faster and less expensive, and they can be deployed at any location. There's no need to wait for several months to go to the facility. And we also did some testing on two chips, an SRAM and an OPAMP, and we observed SEU, SEL in the SRAM, and SET in the OPAMP. So thank you very much for listening to this presentation. We'll send you the webinar feedback form if you have any suggestions to improve the webinar, or any other topics you want to see covered. Please let me know, and if there are any questions, I'll be glad to answer your questions. So feel free to unmute yourself and let me know if you have any questions. Thank you. You're welcome, Jules. Uh, I'm glad you liked it. I would write my email here again as well at scientificpro.com. If you think of a question later, you want to discuss it, please feel free to email me, and I will uh, try to answer. Or if there's any questions now, please feel free. Okay, looks like there are no more questions. So once again, I thank you very much for your attention, and I hope you found this useful. And if not, please send me some suggestions as how I can improve this presentation. I wish you a good afternoon and stay safe. Thank you. Bye.